Hello everyone. For this last video, I'm going to be talking to you about wave-particle duality. So far, we've talked about how Young's experiment proved that light could behave like a wave. And this upset the, at that time, held belief that was held that light acted like a particle. However, later observations by Hertz proved that light could in fact behave like a particle. And it was Einstein who built a theoretical model to describe Hertz's observations of the photoelectric effect. The idea that Einstein came up with that was so ingenious was that light was not only composed of particles, photons, but that each photon held a quantized amount of energy, a set amount of energy, which depended on its frequency. So this really went back to one of the things that Newton had believed, that different light particles behave differently depending on their color, which it turns out was correct in a way. We also learned from the Compton effect that photons have momentum, so that they can collide with particles like electrons. Speaking of electrons, the electron is a really good particle to use because, well, we understand many of its properties really well, and it turns out that because of those properties, it's really good when we're looking at light and matter interactions. So one thing that's really key about the electron is that it has a low mass, and at least when it has low velocity, it has low momentum. So even if a photon doesn't have a ton of momentum, it can still produce a meaningful collision with an electron. Also, the electron has a relatively large charge, at least compared to its mass. Like a proton has the same charge, same magnitude of charge, but it's 1,000 times more massive than an electron. So if you want to actually accelerate an electron to high velocity, you can do that using electric fields for the linear acceleration and magnetic fields to steer left, right, up, and down. So this begs the question, if light can be considered a wave with particle-like properties, could something like an electron be considered a particle with wave-like properties? That's a pretty important question. And there's an experiment that actually answers it really well. So this is the Davisson-Germer experiment, where Davisson and Germer basically had a source of electrons which they fired at a sample of nickel. And what they observed was that the electrons were diffracted. Okay, so it's a slightly different word from what I've used before. But anyway, if you remember back to when we talked about light last week, we talked about the idea of diffraction, where light can essentially bend around corners. So it's a similar kind of thing here, except that the electrons weren't bending around corners, but they were, in a sense, reflecting off of the atoms in the nickel sample. And those electrons that were diffracted create this very interesting pattern that actually tells you about the structure of the nickel. So here's the basic setup. So you can see that the electrons come in along the axis and hit the target and will diffract off at some angle, right? Some angle theta. And then you have this movable detector, which in principle could actually go all the way around the target, although that's not usually necessary. And this detector back in the day was actually like a photographic plate, whereas nowadays it's some kind of CCD camera or something. But in any event, this movable detector will basically move along some arc and then collect the electrons that are diffracted out at that angle. And when you put all the data together, you get an image that looks something like this. In university, I did a course on this using called X-ray diffraction. So it's the same kind of thing, except we're using X-rays, not electrons. But we were looking at patterns like this one and using them to deduce what the actual structure of the sample was, like how, in other words, how were the atoms arranged in space. So although it may look like a bunch of dots, I hope you'll agree that there is some structure to it. And if you learn how to analyze that structure, then it will tell you about the physical geometry of the atoms. So this leads itself to an interesting question, because if an electron is to have wave-like properties, then one of the most wave-like properties you can have is a wavelength. So how should that go? Well, in 1923, there was a physicist named de Broglie who had read up on the Compton effect and was trying to understand it. And he basically said, look, if photons can have a momentum, then surely particles with mass can have a wavelength. Now that doesn't really make sense on its face, but nevertheless, that was his contention. So really, all he did is he took this equation that the wavelength of a photon is equal to Planck's constant divided by its momentum. Okay, so again, you'd have seen this when you read about the Compton effect. And then he said, well, if everything is fair game, then this momentum, we're going to replace that with mv for particles that actually have mass, right? This wouldn't make sense if our particle actually had mass, because like a photon doesn't have mass, it's a massless particle. But in the event where we do have a mass, like such as an electron, then let's make that substitution and see what happens. So it was a pretty radical idea, because again, this is not that long after, so 1923. So this is less than 20 years after Einstein wrote his paper on the photoelectric effect. And so the idea that light was a particle was, I would say at this point, reasonably well accepted. I wouldn't say that people were willing to consider the reverse in the same light, right? To say that an electron has wave-like character is strange. So it almost cost de Broglie his doctorate, in fact, until Einstein actually read his paper and intervened. So I mean, I think at the point where you can actually say, yeah, my buddy Einstein over here says it's right, then that usually ends the argument. But nevertheless, there was a little touch and go there. Let's look at a sample problem. If after all we can calculate if an electron is to have a wavelength, then we should be able to calculate it using some reasonable information. So here's a question: what is the de Broglie wavelength of an electron accelerated from rest through a voltage of 52 volts? 52 volts is next to nothing in terms of accelerating electrons. So this should be quite straightforward. So the first thing we're going to do is remember that any work that the electric field, right? If there's a voltage, that means there's an electric field. So our electric field is going to do work, and that work will then give us kinetic energy. Will give the electron kinetic energy, essentially. Okay, so that's our starting point. So the left side of the equation is simply Q delta V, right? The charge of the electron multiplied by the voltage, the potential difference. And then the right side of the equation is our good old-fashioned 1/2 mv squared, right? The kinetic energy of the electron. So if we do a little rearranging, we get an expression for the speed of the electron. That's fine. I'm not going to actually do the calculations just yet because I'm not done. So I'm going to take that expression and put it into the de Broglie equation, because you can see where I'm at here. I know everything. Okay, clearly the wavelength is something I want to know. The mass of an electron I know, or I can look it up, and and Planck's constant is again known. So all I need to do is find an expression for V. So if I substitute that in, then it kind of looks ugly, keeping in mind that because V is in the denominator, I actually need the reciprocal of my previous expression. And also note that I have a mass underneath the square root sign as well as a mass outside of the square root sign. So those you can kind of combine if you remember your exponent laws. Anyway, when all is said and done, you get this expression, that the wavelength of the electron is equal to Planck's constant divided by the square root of 2 times the charge times the mass times delta V. Now I have to be a little careful here, because technically speaking, the charge on an electron is negative, but by the same argument, the potential difference would also be negative. So these two negatives would cancel out, because otherwise the electron wouldn't actually be, if that were the case, then the electron wouldn't be accelerated. So when I put the numbers in, I'm just going to leave the charge on the electron as a positive, even though I actually know it's negative. only because the same thing would happen with the potential difference, and I don't want to have a bunch of negative signs floating around. It's not really important for the math. Okay, so when I plug in the numbers, I've left off the units here only because I was running out of room, so you can look them up, and I get my value, my wavelength, is 1.70 times 10 to the negative 10 meters, or this is sometimes reported as 1.70 angstroms. That symbol, that A with the little circle above it there, is called the angstrom. It's named after a Swedish scientist, and the A with the circle above it is the letter O. It's not in the English language, obviously, but it is used in this. It's part of the Swedish alphabet. So that's the angstrom. It's not an SI unit, technically speaking. It's such a convenient unit when you're working with things on the order of the atomic scale. Like if you want to know the distance from one atom to the next, you would almost certainly use the angstrom as your unit of choice. So again, this is one of those situations where, depending on what you're studying, you might adopt units that are not necessarily SI, but we just kind of agree we're going to use these angstroms because no one likes writing down times 10 to the negative 10 all the time. It's just a pain in the butt. Okay, so that's kind of what's going on there. All right, so now that we've actually looked at an electron and decided that, yes, it does have a wavelength, and that wavelength is on the order of an atomic spacing, then one thing that we could consider doing is actually building a kind of two-slit experiment, but instead of having slits in a piece of paper that would be appropriate for light because of light's wavelength, we would need to have slits, technically speaking, that are on the order of an atomic spacing. Now that might seem kind of hard, but if you think about it, all you would really need to do for this is use a very thin, crystal. And when I say crystal, I know that you're probably thinking of, I don't know, maybe like a emerald or diamond or something like that. But when I use the word crystal, I actually mean just anything that has a regular periodic structure. So most metals, for example, have crystalline structure. So in this case, if we wanted to look at the interference of electrons, right? If we wanted to actually shine electrons through something and try and produce an interference pattern to see in other words, if electrons behave the same way that light does, well, we need slits that were roughly on the size of the wavelength, right? That's what you saw last week from Young's double slit experiment. If the slits are too large, then you don't get interference. So it's the same thing here. If we're going to have slits that will work with that will produce interference with electrons, we need them to be roughly on the same size as the electron wavelength. So that's the practical consideration. And I'm not saying that's easy by any means, but you can do it. And if you do it, you actually get results that are similar to Young's experiment. In other words, if you set the conditions of the experiment just right, you can actually see that electrons will interfere in the same way that light interferes, passing through two slits. What's strange is that you could, unlike light, where it's not always so easy to get light down to the point where you're only having one photon pass through, one photon going through at a time. You can't always get the intensity so precise. Because of the way that electrons are often made, you can actually engineer things that you actually only have one electron passing through the slits at a time. So if you have your two slits, then logically it would make sense that the electron will either be passing through this slit or through this slit, right? If you only have one electron, it's got to go through this one or this one. So which is it? There's a lot of discussion within the philosophy of physics as to what's actually happening between when the electron approaches the slits, passes through the slits, and then later on hits the screen. If you have two slits, then again, logically, if we're thinking of the electron as a particle, then it would only ever pass through one slit or the other. And yet, if that were the case, then we wouldn't see an interference pattern, because an interference pattern doesn't happen when you have just particles, it happens when you have waves. So what's going on here? Did the one electron split into two pieces and then part went through this one and part went through this one? Or did it actually go through one slit or go through the other? Or did it go through both? Like, how did that work? These are actually pretty difficult questions to answer. And that's why at the end of this video, the part of your work is to watch another video called, what is it called again? Quantum reality, sorry. And it's a little bit long, but it actually goes through the argument and what are 4 possible explanations as to what's happening to the electron. How is it splitting up, or how is it producing this interference pattern? Okay, one thing that the video talks about that I'm going to mention here is that if you actually are able to measure which of the slits the electron goes through. So for example, if you had a little detector at the bottom of the slit that could say, oh yes, the electron is passing through this one, or the electron is passing through this one, then all of a sudden the interference pattern disappears. So you don't get the interference pattern any longer. It's only when there's a certain amount of uncertainty as to whether the electron went through one slit or the other that you actually get the interference pattern. As soon as you make a measurement and you know which slit the electron went through, now that uncertainty is broken and it now behaves as a classical particle, right? Imagine like tennis balls being fired through slits. I think that's the example that they use in the video. So that's really weird, right? It's really weird that somehow our action on this system, right, whether we take a measurement or not, or how we take a measurement, actually makes a difference as to what happens on the other side of the experiment. It's pretty weird stuff. What's fun about this, this idea of interference is that while you can imagine an electron is probably the smallest particle-like thing that you would ever want to think about, interference can actually occur with much larger particles. So yes, it's been observed with an electron. That was done a while ago. But more recently, it's been done with particles as large as something called carbon-60, which is basically, if any of you play soccer, a carbon-60 molecule is a soccer ball where at each of the places where the stitching meets up would be a carbon atom. So if you actually count all those places on a soccer ball, there are 60 of them. So that's what a carbon-60 molecule looks like. It looks like a soccer ball. They have actually observed with a carbon-60 molecule, which is like quite large, certainly much larger than an electron, they have observed those interference effects. So even though this is something that we don't normally see, that we don't see like in our daily lives because we're too large, nevertheless, you don't have to be as small as an electron. You only have to be as small as a carbon-60 molecule, which is still pretty small. Thanks very much, folks. Here's your homework. I only want you to look at these 3 questions as well. There's going to be a video linked. Let's see if I can get the side right. That one? I'm going to go with that one. It's probably the other one. But check it out. And yeah, I'll see you next time. Don't forget to like, share, and subscribe.